Hello everyone, this side Manisha Mishra, Assistant Professor in Mathematics, Applied Science Department at St. Andrews Institute of Technology and Management, Gurgaon. This college is affiliated to Maharishi Dayanand University. So today I will discuss the topic Cauchy residue theorem, and about Cauchy residue theorem I told you in our previous lecture. So basically today I will share few applications of Cauchy residue theorem, and there will be an exercise also here. So you will done your exercise. So there is an first there is a method of residue at z is equal to infinity. So how we will find our residue at infinity? There is also a part of residue. So residue at infinity is equal to limit z tends to infinity minus z into fz. That means if you have to find your residue at infinity, so you will just multiply by minus z into your fz is your given function, or residue of fz is equal to minus 2 of pi I integration fz dz. So there is an example here, and this example is just for residue at z is equal to 0. So first, this example is related to find the residue of fz at infinity. After that, we will discuss our above example. So fz, we have zq upon z square minus. So we need to calculate our residue at infinity. So first, we have to write our function as 1 by z type. So fz is equal to zq upon z square minus 1. So just taking z square common, so 1 minus 1 upon z square. Z cube, z cube and z square, just 2z will be cancelled out. So z into z upon 1 minus 1 upon z square. So you can write your 1 minus 1 upon z square as 1 minus 1 upon z square to the power 1. If we will move our 1 minus 1 upon z square in the numerator, then it will be 1 minus 1 upon z square to the power minus 1, right? So we know that binomial expansion. So binomial expansion is 1 plus x to the power n is equal to 1 plus nx plus n minus 1 upon 2 factorial into x square upon 2 x square, right? So apply this theorem here. So 1 plus n, 1 plus x is your minus 1 upon z square to the power minus 1 is your n. So 1 plus nx, 1 plus n is minus 1, x is minus 1 upon z square. So minus 1 will be positive sign, and it will give 1 upon z square. Plus n minus 1 upon 2 factorial into x square. So that will also give you 1 upon z to the power 1, plus and so on. So this z is outside, you just multiply inside the bracket, and you will get z plus 1 upon z plus 1 upon z cube plus and so on. So just write, look here, residue at infinity. So your residue at infinity is equal to minus coefficient of 1 by z, because if we will if you put z is equal to 0 here, z is equal to infinity here, so infinity plus 1 upon z, so all will be 0. So coefficient of 1 upon z. So coefficient of 1 upon z, you can see here 1. So minus 1 is your final answer. So this is the method to find the residue at infinity. Now, our previous question. Find the residue at z is equal to 0 of z into cos 1 by z. So I told you where cos z sin z series is given, then you will expand your series. So cos 1 by z series is 1 minus 1 upon 2 factorial into 1 upon z square plus 1 upon 4 factorial into z to the power 4 minus and so on. There will be an alternative sign. Positive, negative, positive, negative, right? And cos z series always an even term series, and it will start from 1, and sin z series always a odd term series or odd power term, and it will start from x. So z minus there is a z is here outside, so just multiply inside, then z minus 1 upon 2 factorial z upon z square plus 1 upon 4 factorial z upon z to the power 4 minus and so on. So z minus 1 upon 2 factorial 1 by z plus 1 upon 4 factorial 1 by z cube and so on. So just look at here, what is the residue of this function? This is a Lorentz series. So residue, that means you are getting a pole, and pole is pole of order 1 here. 1 by z means I have already told you that you can write the coefficient of negative power 1. That means a minus 1. So what is the value of a minus 1 here? A minus 1 value is 1 up minus 1 upon 2 factorial. So that will be your residue. So a minus 1 is equal to 1 by 2. That means residue of z into cos 1 by z at z is equal to 0 is minus 1 upon 2. If you are getting a simple pole or pole of order, then you can apply your formula. But here there is a direct Lorentz series, so you can just apply your one method that I have told you, that residue of fz will be your a minus 1. That means negative power coefficient. Right. Now, there is another example. Using residue theorem, evaluate this integral where C is the circle, mod Z is equal to 3. So this is your, I think, 15 marks question, will be your 15 marks question. And this type of question will be asked in MHAS Gannon University final semester exam. So let's see, using residue theorem, that means suppose guys, how you will differ between residue and Cauchy residue theorem, right? If integral is given, right, integral is given, then you will apply Cauchy residue theorem. If integral is not given, only directly fz is given, then no need to apply residue Cauchy residue theorem, because question will say that find residue, right, of fz. So just apply your residue formula there. But if integral is given, then you will apply your Cauchy residue theorem. That means you have to calculate your integral value, right? So now question is 1 upon, you have to evaluate this integral 1 upon 2 pi I into this integral e to the power zk dz upon this one, right? So mod z is equal to 3 is a given circle. So first we need to calculate our pole. So for the poles, you will put denominator is equal to 0. So write denominator is equal to 0. So z is equal to 0 is a pole of order 2, because z square is equal to 0. That means you will get 0, 0 2 times, right? So z is equal to 0 is a pole of order 2, and this bracket z square plus 2z plus 2 is equal to 0. Then you will calculate this by your discriminant method. So just calculate. So discriminant method is z is equal to there is a quadratic equation ax square plus bx plus c is equal to 0. So this is your quadratic equation, z square plus 2z plus 2 is equal to 0. So this method is applicable only for quadratic equation. So method is x is equal to minus b plus minus square root of b square minus 4ac upon 2a. Just apply here. Minus b means minus 2 plus minus square root of b square 2 square minus 4ac, 4 into 2 into 1 upon 2a. 2a is 1, so 2. Now z is equal to minus 2 plus minus 2 square means 4 minus 8 upon 2. So just minus 4, and in complex number, minus 1 value is always iota square. So you can write here iota square. So minus 2 plus minus 2i upon 2. So you guys, you will get minus 1 plus iota minus 1 minus iota are the simple pole, because these are differ from each other. So pole of order 1 या फिर simple pole. Now after that we need to check that these poles, these are 4 poles here, and these poles are lie inside the circle or not. So check, given circle is mod z is equal to 3. So first draw a circle of radius 3. This is your circle of radius 3. And check z is equal to 0. So z is equal to 0 pole will lie on origin. That means it will inside the circle. So we can say that all the poles are inside the given circle. So now second pole is minus 1 plus iota minus 1 minus iota. So just check these poles. So z is equal to -1 plus iota. That means if you will compare x plus iota, y is equal to -1 plus iota, then you will get x is equal to -1 and y is equal to 1. So -1 and 1 coordinate will lie inside the circle of mod z is equal to 3. So here this point -1 and 1 that means -1 plus iota will lie inside this circle. Now -1 minus iota, so you can compare. So x is equal to -1, y is equal to -1, so both are -1. That means this point will lie in your third quadrant. And third quadrant, so this is also inside the circle. So all the poles, that means all the four poles are lying inside the circle mod z is equal to 3. That means you will calculate residue. You have to calculate residue at these points. If these points does not lie inside the circle, that means your residue value will be 1. So for the residue 0, I will discuss more examples for in our further session. So just look at this one. So find residue of fz at z is equal to 0. So at z is equal to 0, so 0 is coming, 0 is a pole of order 2, that means n is equal to 2. So just apply pole of order n formula here. So residue at z is equal to 0 is equal to limit z tends to 0, 1 upon n minus 1 factorial d to the power n minus 1 upon dz to the power n minus 1 z square into fz. So guys, put n is equal to 2 here, and z is square into fz. Fz will be your e to the power zt upon z square into z square plus 2z plus 2. So where fz is coming from? Fz is coming from here. This is your fz. Z is e to the power zt upon z square into z square plus 2z, 2z plus 2. So this will be your fz. So just write here fz, and now just simplify. So z square cancelled out, and d upon dz. That means you have to differentiate our function with one time. So u upon v fraction form. So just apply your division rule here. So v dot du. So v will be your z square plus 2z plus 2 dot du. Du means e to the power zt differentiation, and that will be your t into e to the power zt minus u means e to the power zt, and dv means z square differentiation 2z, 2z differentiation 2, and 2 differentiation will be 0 because this is a constant term, and constant term differentiation is 0 upon v square. Right, now apply limit. So just put z is equal to 0, then you will get t minus 1 upon 2. This is the value of residue at z is equal to 0. Right, now there are more two poles. So second pole is z is equal to -1 plus iota. So residue at -1 plus iota, that means this is a simple pole. So you will apply your simple pole formula here. So limit z tends to -1 plus iota is equal into z plus 1 plus z plus 1 minus iota. So you guys are finding your residue at this point. So just put it left hand side, then you will get z plus 1 plus minus iota into fz, and your fz is e to the power zt upon this one. So z square plus 2z plus 2, you have already find its factor, and its factor is z plus 1 minus iota, z plus 1 plus iota. So you can write z square plus 2z plus 2 as z plus 1 minus iota into z plus 1 plus iota. So this will be cancelled out, and only these value will be here, and put z is equal to this one. So you will get, after solve this steps, you will get your residue e to the power minus 1 plus iota into t upon 4. Now, same as it is, find your residue at z is equal to -1 minus iota. So limit z tends to -1 minus iota, z plus 1 plus iota into fz, right? So just put the value of fz, and you can write z square plus 2z plus 2 like this one, and this bracket will be cancelled out, and apply the limit. So finally you will get your residue at this point, this one. Now we have already calculated our residues. Now we need to calculate integral value. So for the integral value, that means Cauchy residue theorem will be applicable. So now by the Cauchy residue theorem, you can write integration this one into dz is equal to 2 pi I into sum of residues, right? So we need 1 upon 2 pi I. So just you can write 2 pi I here in is equal to sum of residues, and sum of residues at 0 this one value, at z is equal to minus 1 plus iota this is value, and z is equal to minus 1 minus iota this one. Just add all of them, right? So that value you can solve further if you want to solve, otherwise leave it as it is. That value will be your answer. Now if integral there will be asked a 15 marks question in your final semester exam that evaluate the following complex integral. Yeah, evaluate complex integral. So you will evaluate your complex integral always by Cauchy residue theorem. Now there is another example here. There is an exercise actually. These are for 3 to 4 questions, and you answer. Actually, I am already provide you answers here, so you can match your answer is correct or not, your solution is correct or not. And first question is actually evaluate the following complex integral, right? So first question is integration 1 minus 2z upon z minus 1 z minus 2 into dz. So you will calculate your integral value. That means these questions will be solved by Cauchy residue theorem. Now fz will be your 1 minus 2z upon z minus 1 z minus 2. So first you will find your poles, that means put denominator is equal to 0, and after that you will check that this which pole lie inside the circle. So z is equal to 0, we can see here z is equal to 0 is a simple pole, z is equal to 1 is a simple pole, and z is equal to 2 is a simple pole, right? Now all of the three poles, there is a question that all are the three poles are lying inside the circle or not. So z is equal to 0, you can see 0 can lie inside the circle 1.5, 1 can lie inside the circle 1.5, means z is equal to 0 and z is equal to 1. Both of the poles will lie inside the circle mod z is equal to 1.5, but z is equal to 2. Z is equal to 2 does not lie inside the circle mod z is equal to 1.5. So at z is equal to 2, the value of the residue will be 0. So you will calculate your residue only at z is equal to 0 and z is equal to 1. You don't need to calculate your residue value at z is equal to 2. You can write directly that this point does not lie inside the circle mod z is equal to 1.5. So we can say that residue of fz at z is equal to 2 will be 0, right? So just solve this question. Now there is another question, z plus 1 z minus 1 upon z plus 1 whole square into z minus 2 into dz. So for poles you will write z plus 1 whole square is equal to 0, z minus 2 is equal to 0, right? So z plus 1 whole square, that means z is equal to minus 1 minus 1. This is a pole of order 2, and z is equal to 2 is also a pole of order 2. Now our circle is given z minus I is equal to 2. That means this is a circle of radius 2 having center at x is equal to 0 and y is equal to 1. You can check here z minus 1, z minus iota, that means x plus iota y minus iota, that means x plus x, you can write it x plus y, and iota is common, y minus 1. That means you just try to understand x plus y minus 1 into iota is equal to 0. That means this is a circle of radius 2 but center at 0 1. So you will draw a circle which center have 0 1. So 0 1, that means it will lie on y axis, and when you draw your circle you will check that minus 1 minus 1 and z is equal to 2 are lying inside the circle or not. If it is outside the circle, that means residue will be 0, so no need to calculate residue at these points. But if it will lie inside the circle, then you will calculate your residue as you have already done in our previous sessions. Now there is another one, z square minus 1. So you will check your pole, and this is a circle, z minus 1 is equal to 1. That means radius is 1 and center is 1 0, right? So just check all of these questions. Now there is another example here. integration dz upon z square plus 1 z square minus 4, where c is the circle, mod z is equal to 1.5. So just put denominator is equal to 0, your fz you can see 1 upon z square plus 1 z square minus 4. So for 4 poles, put denominator is equal to 0, right? So z square plus 1 z square minus 4 is equal to 0, z square plus 1 is equal to 0, z square minus 4 is equal to 0. So you are getting z is equal to plus minus iota and z is equal to 2 minus 2 are the simple poles, right? So you can see here it is clear that z is equal to 2 minus 2 does not lie inside the circle mod z is equal to 1.5, because 2 value is greater than 1.5. So it is clear that this does not lie inside the circle, but z is equal to iota and minus iota. So you have to check now. Z is equal to iota, you can write x plus iota, y is equal to y, x is equal to 0, 1. So check 0, 1 are lie inside the circle. Yes, this will be lie on y axis. Here z is equal to minus iota, x plus iota, y is equal to minus iota, x 0, y 1. So 0 minus 1 will be your in our fourth quadrant. That means both of the poles will lie inside the circle. So you will calculate your residue at these poles. Now residue at z is equal to I. So limit z tends to I. This is simple pole. So apply simple pole formula here. Z minus I into Fz. So limit z tends to I. Z minus I into Fz means 1 upon this one. So limit z tends to I. Z minus I upon this one, and this value will be cancelled out. Z square plus 1, you can write z plus 1, z minus I minus 1. You have already factored this quadratic equation. So you are getting minus 1 upon 2i into minus 1 minus 4. 4 plus 1, 5. 5 minus 5 into 2i minus 10i. And you can write minus 1 as iota square. So you are getting your residue value as I upon 10. Now, residue of fz at z is equal to minus iota. This is also a simple pole. So apply simple pole formula. Limit z tends to minus iota z plus I into fz, right? So limit z tends to minus iota z plus I, fz is your this one, and z square plus 1, you can write z plus I, z minus I. This will be cancelled out and apply the limit. So after applying the limit, you are getting 1 upon minus iota whole square minus 1. So minus 2i iota square, and iota square value is minus 1 minus 4. That means you are getting 1 upon 10i. So just multiply in denominator and denominator by iota, then you will get your answer minus iota upon 10, right? By Cauchy residue theorem, we need to calculate our integral value, and we have our integral value is 2 pi I into sum of residues. So 2 at 2 and minus 2 residue is 0. So 0 plus at iota residue value is iota upon 10, and at minus iota residue value is minus iota upon 10. All will be cancelled out and you will get your answer 0 here. Sorry, there is a mistake here. 2 pi I into 0, then you will get 0 here. So this will be correct, and write here 0, right? That value does not your answer. This is a wrong answer, and this is a wrong answer. Just write here 0, right? This is the wrong answer. So 0 is your final answer, right? So here, same as it is question, there is another question here. So 4z square minus 4z plus 1 upon z minus 2z square plus 4 into dz. So just check, this question and above question both are same, matlab method is same. So just apply same method here. So your answer is also 0. So just try to solve these questions. There are 4 to 5 questions in above, and one question is also here. So all questions are related to Cauchy residue theorem. So just to try to solve these questions and tell your answer with my answer, and I will provide you a solution of these questions. So just solve these, and thank you.